In the last class, we discussed about stress strain curve diagram and how we will represent it and how the specimen will change from the point to point. That means from limit state of proportionality to elastic limit to upper yield point to lower yield point, and how specimen is changing. Okay, so based on that, we will draw the stress strain diagram for different materials. As we all know, already we come across the topic. So the stress strain curve will represent the material property. Okay, for time being, so let us revise a bit. In the last class, we discussed about here we will have our limit state of proportionality. The value what we are getting here is our Young's modulus, right? So after that, we will have elastic limit, and after that, we will have upper yield point. From upper yield point, there will be a sudden drop of stress. So this is called our lower yield point, right? So this is our lower yield point. And this is our plastic limit, and this is our ultimate stress, and this is our fracture breaking point. Okay, so based on this graph, we will have the zones from 0 to B is linear. Sorry, from 0 to A, all this portion is called as linear elastic zone. Okay, the why we will call it as linear elastic means here the line is very much straight and it is making 45 degrees with the horizontal. So that's why we are taking it as linear elastic. From 0 to B, that is origin to B, is called as elastic zone. From here, because there is a bit curve, so that's why it is called as elastic zone. From here to here, C to D is yielding zone. So remember the shape. The shape is very much important for further drawings. So yielding zone will look like this, right? There is a sudden drop. So elastic will look like this, yielding look like this, and our plastic zone D to E is called as plastic zone. C to D is a yielding zone, and D to E is plastic zone. So, okay, plastic zone. This is called as D to E is plastic zone. So plastic zone is represented by in this way, right? Okay, and next E to Z. So E to Z is called pre-ultimate stress zone or hardening zone. This is called as hardening zone, and this is called as softening zone. Stress softening zone. Because why? Because we will call it as stress softening zone, because here the failure will happen. So that's why the material will become soft and the stress will fall. So that's why we will call it as stress softening zone. But here stress will increase with the time. So when compared to upper yield point, here in ultimate stress, the material will take more stress. So that's why we will call it as strain hardening zone. So it is also called as necking zone. Necking zone. So in this way, we will represent different materials, right? So linear elastic means this is it. So now we will call this graph as linear elastic, and this one is, if the material only takes the stress alone, then we will call it as rigid. Okay, so rigid material will not undergo any deformation. So that's why the complete x-axis, that is nothing but our strain is completely zero. But in case if it is ideal fluid, we will call it as, we will represent it on strain. That means x-axis. Why we will represent x-axis? Because the fluid takes only the strain. So that's why it is ideal fluid. It can't take any stress inside. So that's why it won't resist any force. So that's why we will represent it on x-axis. It will represent it on y-axis if it is completely a rigid body. So rigid body takes up to certain, rigid body takes only the stress. So after that, if something is drawn like this, what we will call it as? So we already discussed, if the line is horizontal, then what it is? Plastic zone. So right, so plastic zone. So up to here is rigid. After that, it will become plastic. So that's why we will call it as rigid plastic. Okay, so in this way, we have already discussed that softening will occur in this way, and strain hardening occurs in this direction, softening occurs in this direction. That means the slant of line. So if it is projected upwards, it is stress hardening. So for timing, here this is linear elastic strain hardening, and this is strain softening, right? So linear elastic strain softening. So in this way, this is linear elastic and plastic, because this is a horizontal line, right? So the plastic zone is represented by this way. So in this way, the stress strain curve defines the material. So in this format, we will understand how the diagrams are, how the charts will define the material properties. So this is very much important in any exam. So in further, you have to answer this in comment section. So what is this material and what is this material? So okay, so please answer in the comment section. Okay, so there is another property called as resilience. Resilience is nothing but the strain energy, the strain energy stored in a body is called as resilience. So resilience. And proof of resilience. Proof of resilience means the maximum strain energy. That means strain energy is nothing but the work done. Work done is defined by half into P into delta. That means load into delta is the deflection. So from where we obtained it is nothing but stress strain curve diagram. If you draw a line, if you draw something for a brittle material, if you draw a stress strain curve for a brittle material, the area covered under the stress strain curve diagram is nothing but strain energy. That is the work done. Here the load, here the delta. So it will look like a triangle. So the work done will be the area of this diagram. So for time being, we will consider it as nominally, and our BH is B is nothing but is our base delta deflection, and our height will be P. So the strain energy is RP into delta. Okay. In case if it is a stress strain curve diagram, what is the work done? So work done will be half into stress into strain. Okay, so the strain energy units are joules or Newton per meter. So there is another definition called toughness. Toughness is nothing but the area covered up to the breaking point. So area covered up to the breaking point is toughness. The area which is covered up to breaking point is toughness. So which is up to the elastic limit. The area covered up to elastic limit is resilience. So the maximum resilience. The proof of resilience means maximum strain energy. If a material is ductile in nature, it will have a large plastic zone, plastic deformation. So before the failure, it will have a large area covered under stress strain diagram. But that means if 5% is more, if 5% plastic deformation is there before it's getting failure, then we will call it as ductile material. If the stress strain curve has very less area before failure, less plastic deformation before failure, that is 5% before, so we'll call it as brittle material. So based on the stress strain curve diagram, we will define a lot of material property. So that's why the stress strain curve plays a major role. So let us So let us revise everything once. So let us summarize everything. So linear elastic zone is nothing but 0 to A. So from here to here, Hooke's law is valid. Stress is directly proportional to strain. So stress is directly proportional to strain. So up to where it is up to limit state of proportionality, because in B, after B is nothing but is our elastic limit. So after reaching limit state of proportionality, it will go to elastic limit. The material will go to elastic limit. But in the elastic limit, if you remove the load, it will regain its own shape. But some distortion will be there. So that's why we will consider as the limit state of proportionality is valid. Up to limit state of proportionality only stress strain is valid. So that's why we will consider limit state of proportionality for stress Hooke's law. So based on this, Hooke's law will be valid up to limit state of proportionality. We will discuss about it in the next video. And the C is nothing but is our upper yield point and D is lower yield point. So now the yielding zone is represented by single falling line. Okay. Next, plastic zone will be represented by horizontal zone, and hardening zone is represented by rising curve, and softening zone is represented by falling curve. So we need to understand this clearly to answer different charts. For timing, you need to answer this linear elastic. What is it? Linear elastic and yielding. So please answer the question about this question. Okay. So in this way, we need to understand the whole stress strain curve diagram. So thank you very much for watching.